So we're going to start where we left off, and we're going to think about peptide bonds. So this is a special name given to the amide bond between the alpha carboxyl group of one amino acid and the alpha amino group of another. When we think about peptide bonds, we recognize that it's actually the name that's given to a short polymer of amino acids joined by peptide bonds. They're going to be classified by the number of amino acids in the chain. For example, a dipeptide contains 2 amino acids. A tripeptide contains 3. A polypeptide would contain many. And a protein is a biological macromolecule of molecular weight 5,000 grams per mole or greater, consisting of 1 or more polypeptide chains. We need to be able to draw the peptide bond between serine and alanine. In order to do so, we have to recognize that peptide bond is an amide bond. So take a moment, think about the structures of serine and alanine, and then think about drawing an amide bond between them. If you need to, press pause and then come back to check your work. So here we see the carboxylic acid of the serine, which will form an amide bond with the amino group of the alanine. That peptide bond is shown with the bond in red. By convention, peptides are written from left, beginning with the free ammonium group and ending with the free carboxylate group on the right. Primary structure then is the sequence of amino acids in a polypeptide chain, reading from the N-terminal amino acid to the C-terminal amino acid. This amino acid analysis then can occur when we hydrolyze a polypeptide. Typically we do this using 6 molar HCl with elevated temperature, and then we can do quantitative analysis of the hydrosylate by ion exchange chromatography. In order to account for the geometry that we observe within peptide bonds, Linus Pauling proposed that a peptide bond is most accurately represented as a hybrid of 2 contributing structures. So the hybrid has considerable carbon-nitrogen double bond character, and rotation then about the peptide bond is restricted. Now in reality, this is only about 40%. However, what we need to understand is that this resonance is something that we've already seen before and you should be comfortable drawing. So when we think about proteins as a whole, we're going to be thinking about the primary structure, that is the order and sequence of amino acids, the secondary structure, which has to do with intermolecular forces, forming alpha helix or beta sheets, and then tertiary structure, which incorporates things like disulfide bonds, as well as quaternary structure, where we have multiple subunits joining together. So the primary structure is a sequence of amino acids in a polypeptide chain. This is read from the N-terminal amino acid to the C-terminal amino acid. When we think about this for proteins, it's important that we recognize that the stereochemistry of the amino acid matters. It's also important for us to understand that at a given pH, the structure of the amino acid matters. So for example, at low pH, right, I'm going to have a high concentration of what's shown in pink. As my pH creeps towards neutral, I'm going to have a high concentration of the zwitterion. As my pH increases towards basicity, or pH of 14, I'm going to have a high concentration of the structure that's shown in green. Because we talked about the geometry of peptides, I want to remind you of the resonance contribution, which contributes both to the stabilization and also what we expect to see as the trans nature of the amide bonds in proteins. When we think about proteins themselves then, we're going to think about ways that we can analyze them. So one of the ways is the cleavage of a peptide bond formed by the carboxyl group of methionine. If we cleave that bond, we can separate a protein into segments. This is actually done in nature by several protein cleaving enzymes that are used to catalyze the hydrolysis of specific peptide bonds. Enzymes such as trypsin or chymotrypsin. Note, you need to be familiar with where trypsin and chymotrypsin cleave the specific amino acids that they catalyze the hydrolysis of a peptide bond formed by the carboxyl group of. You also need to be familiar with the Edmond degradation. This is what cleaves the N-terminal amino acid of a polypeptide chain one by one. You don't have to know the mechanism in this case, but you need to be familiar with the idea that you can do analysis on proteins to have an understanding of their primary structure. The secondary structure of proteins is the ordered arrangements or conformations of amino acids in localized regions of a polypeptide chain. To determine In order to build a model what would create the greatest stability, Pauling and Corey assumed that all 6 atoms of each peptide bond lie in the same plane and have a trans configuration, and that there's hydrogen bonding between the NH groups of one peptide bond and a carbonyl group of another peptide bond. On the basis of model building, then, Pauling and Corey proposed that 2 types of secondary structure should be particularly stable, an alpha helix and an anti-parallel beta sheet. An alpha helix is a type of secondary structure in which a section of polypeptide chain coils into a spiral, most commonly a right-handed spiral. There are structural features of the alpha helix, including 3.6 amino acids per turn of the helix, each peptide bond being trans and planar, the NH groups of all peptide bonds pointing in the same direction, which is roughly parallel to the axis of the helix, carbonyl groups of all peptide bonds pointing in the opposite direction, also roughly parallel to the axis of the helix, and then the carbonyl group of each peptide bond as a hydrogen bond to the NH group of the peptide bond 4 amino acid units away from it. All R groups then point outward from the helix. So if we look at this representation of an alpha helix, we can see some of those structural features come into play. The anti-parallel beta sheet, or beta pleated sheet, consists of adjacent polypeptide chains running in opposite directions. Each peptide bond is planar and has the trans configuration. We also observe that the carbonyl and the NH groups of the peptide bonds from adjacent chains point towards each other and are in the same plane so that hydrogen bonding between them is possible. All R groups on any one chain alternate above and below the plane of the sheet. There are 2 types of beta sheets, anti-parallel and parallel. You need to be able to recognize the type of hydrogen bond that exists for each of these, as well as the orientation of the N and C terminus. Tertiary structure is the 3-dimensional arrangement in space of all atoms in a single polypeptide chain. Disulfide bonds between the side chains of cysteine play an important role in maintaining tertiary structure. The last component of protein structure we're going to talk about is quaternary structure. This is the arrangement of polypeptide chains into a non-covalently bonded aggregation. A major factor stabilizing the aggregation of polypeptide subunits is the hydrophobic effect. The hydrophobic effect is the tendency of nonpolar groups to cluster together in such a way as to be shielded from contact with an aqueous environment. As we see here, there are a variety of different types of proteins, both including only alpha helices in their structure, or only anti-parallel beta sheets, or sometimes combinations of the 2. A beautiful example is hemoglobin, which consists of 2 alpha chains and 2 beta chains. Notice, though, the number of subunits can vary, all the way from 2 subunits up to an example such as the tobacco mosaic virus protein disk, which has 17. When we think about the primary through quaternary structure of proteins, a really elegant experiment that divulged this was Anfinsen, who looked at ribonuclease. This is an enzyme that hydrolyzes RNA and is composed of a single polypeptide chain with 124 amino acids. 4-disulfide, or cysteine, linkages are observed in the active enzyme that stabilize the 3-dimensional structure. This enzyme functions only when its tertiary structure is properly aligned. So here's an example of ribonuclease. Here are the 2 chemicals that Anfinsen used for his experiment to disrupt the enzyme's 3D structure, urea and beta-mercaptoethanol. This is what native ribonuclease looks like, and this is what denatured reduced ribonuclease looks like. Anfinsen then used dialysis to separate the chemicals from the enzyme in different orders. Here you see 3 of his experiments. Here's what Anfinsen discovered. By adding either one of these 2 chemicals to the surrounding medium, it is not removed during dialysis. So in essence, Anfinsen could remove either the urea or the beta-mercaptoethanol in any order that he chose. The order then made a big difference in the enzyme's ability to recover from the treatment. When we're talking about proteins, it's important for us to consider coenzymes as well. You're going to notice these as some of the major dietary components, the vitamins that are necessary for health. We'll talk about that in just a little bit. Last thing for today, please check out Fold It as an opportunity to explore the intramolecular forces and the way that they impact the way that proteins fold. Next time we'll talk about nucleic acids. Have a great day.